Solve a few equations now that are not linear and not quadratic. It turns out that we'll use many of the methods that we've learned before. That is, we'll factor, or we'll attempt to factor as our first choice. If we can't factor occasionally, we can put an equation into quadratic form and solve by using the quadratic formula. We'll see that kind in just a little bit. Here's one where we can factor. Now, when we're faced with this equation, we put all the terms on one side of the equation and go about our business of factoring. Now, we saw a third-degree equation earlier where we took out a common factor and the other factor became quadratic, but it's just kind of following your nose through the factoring process here. The common factor here is 3x squared. When we remove the 3x squared, we get x squared minus 16. The difference of squares, you see, which factors into x plus 4 times x minus 4. Then we ask ourselves the question, what value of x will cause each factor to become 0? And for this factor, when x itself is 0, the factor becomes 0. So this solves the equation. When x is negative 4, this factor is 0. When x is 4, this factor is 0. Now, notice that since we have two factors of x here, that 0 is a repeated solution. There are actually 4 solutions here. Only 3 of them are distinct. The 4 solutions are 4, negative 4, and 0 appears as a solution twice. All right. In this next one, notice that we're faced with 4 terms. Now, we're faced with 4 terms, and our prescription for factoring was first to look for a common monomial factor, and we see no common factor for all 4 terms. The next thing we look for is to factor by grouping. Now, by grouping, we pair our terms this way, and in looking at these two terms, x squared is a common factor. When we take out x squared, we're left with x minus 3. Now we look at these two terms. Now, the common factor, we see a 3 here, and there's a 3 in 9. The common factor is either 3 or negative 3. Now, with a little bit of experience, we understand that when we factor by grouping, we are targeting a secondary common factor. That is, once we get to this level, we're looking for a common factor which is a binomial. So we're looking to factor here in such a way that we'll have a binomial just like this one. So since we're targeting our factored form here to have x minus 3, you see, instead of taking just a 3 out here and leaving negative x, we'll take out the negative 3. You see, because of this binomial target that we're after. So we take out the negative 3, we're left with x here. We take negative 3 out of 9, and we're left with a negative 3. And now, of course, in this term and this term, we have x minus 3 as the common factor. Take x minus 3 out of this one, and we're left with x squared. X minus 3 out of this term leaves the negative 3. Now we're in a factored form. And as such, we ask ourselves what value of x causes each factor to become 0. And it's pretty obvious in this one that x needs to be 3 to cause the factor to become 0. Here, we don't know perhaps just by observation, but what we can do is set up the little linear equation. Actually, it's a quadratic equation here, but it's a little equation to help us tell the value of x that causes 0 to occur. Here, x squared minus 3 is 0. Separate the x squared and the 3 and use the square root property, and we have this. So x is plus or minus the positive or negative square root of 3. So here are our 3 roots. In this problem, now notice it's a 4th degree equation, and we're going to solve by factoring if we can. We're going to take an approach similar to the approach that we take in using quadratics. This one turns out to be quadratic in form, and we'll look at what that means in just a little bit. But just factor it as though we had a quadratic equation. You know, x squared times x squared gives x to the 4th, so those are the factors we'll write as the first parts of our binomials. And then we look at the signs, and we just follow the same procedure that we do normally with trinomials that are quadratic. Well, we factor into x squared minus 3 times x squared minus 1. The x squared minus 1 is the difference of squares, so we factor into x plus 1 times x minus 1. The x squared minus 3, just as we saw earlier, we set equal to 0, and we use our extracting square roots, or the square root property, to find x to be plus or minus the positive or negative square root of 3. And our other roots are found here very easily. The x that causes this factor to be 0 is negative 1. The x that causes this factor to be 0 is 1. Now, let's take the same equation and rewrite it over here and look at it in a somewhat different way. Now, what we want to do is write this fourth degree equation in quadratic form. Now, notice this, this sort of clever way of rewriting this. X to the fourth we think of as x squared squared. Okay, so we have a quantity squared here, which is the idea in a quadratic equation. We have a variable which is squared, you see. Now I can think of x squared, you see, as a separate factor here. Now look at this factor, same factor here. You see, we have that factor squared and that factor to the first degree. You see, it's sort of quadratic in form here, isn't it? It's taking that, that same pattern that a quadratic equation takes. Now it really takes on that pattern if we let some other letter stand in for x squared. Let's let u stand in for x squared. Then replacing the x squares with a u, we get x squared minus, excuse me, we get u squared minus 4u plus 3 is equal to 0. And now it really is quadratic. Well, this isn't exactly the same equation that we started with because we let one letter stand in for another. But let's see how we would approach it. What we could do, you see, is solve this quadratic equation for u. And we would find u to be either 3 or 1. Now, we don't want to know what u is, though. We want to know what x is in the original equation. So we go back, and we know that u was standing in for x squared. So let's do the reverse replacement. Let x squared come back into the problem. This x squared then is equal to 3, and x squared is equal to 1. Well, by extracting square roots in both parts, x squared is either the positive or negative square root of 3, or, x is either the positive or negative square root of 3, or x is the positive or negative square root of 1. Of course, this gives us 1 and negative 1, and this gives us the plus or minus the square root of 3, as we saw earlier. So either of those methods is workable here for this particular problem, but this technique of rewriting an equation in quadratic form, when it's not really a quadratic, is an interesting technique to approach some problems that are of the fourth degree, and actually higher degrees as well. All right, here's one more. Now this one, notice, has a fractional exponent here on the variable. Now that implies that we have a radical involved in the problem. And generally, when radicals are involved, we isolate the factor or the term involving that radical. Here, for example, we can begin our process by taking this constant and kicking it out, that is, add 16 on both sides to get this. We can further isolate the x term or the x factor by dividing on both sides by 4. Now, when we do that, we get x to the 2/3 power is equal to 4. Now, and I'm reluctant even to show you the next step because I don't want to give away a secret. It's a nifty little trick to perform here. We're trying to isolate x. That's the whole idea in solving equations. You try to isolate the x, you're making the equation tell you the value of the variable. Well, in order to isolate the x, very simply what we can do, since we're allowed to raise both sides of an equation to some exponent, you see, we just have to choose our exponent carefully. The exponent we're going to choose to raise both sides to is the reciprocal power of this. You see, it's just an interesting piece of trickery, isn't it? Raise this to the reciprocal exponent, and what happens when we raise powers to powers? Well, we multiply exponents. This fraction times its reciprocal will give us 1. Gee, we've isolated the x on the left side of the equation. Well, all of the activity then switches to the right side of the equation where the constant was. And that's now the situation where if we raise this side to the 3/2 power, we raise this side to the 3/2 power. Now, the fractional exponent implies really two operations, remember. Here we're raising to the third power, or as we think of raising to the cubing, and here we're square rooting, and we can do either of those first. So if we take the square root of 4 and then cube the result, we'll have an answer here. The square root of 4 is 2, 2 cubed is 8, 8 is the result. Now, it's important here when raising both sides to a power to verify that we didn't create an erroneous root by raising both sides to some power. Occasionally that will occur. So it's wise to go back with this, this root, this solution, put it back into our original equation and see if we have truth. Let's see if we can do that right quick, just mentally. If 8 is in place of the x, then we have 8 to the 2/3 power. That means square and take the cube root of it. The cube root of 8 is 2. 2 squared is 4. Let's see, 4 times 4 is 16. 16 minus 16, 0. 0 is equal to 0. Well, this is indeed a correct solution. Here's an equation involving a radical. We approach it in much the same way we did with the earlier problem involving a fractional exponent. All right, we isolate the term containing the radical. Here we would add the radical on both sides and get this equation. Now what we intend to do is square on both sides to clear the radical. You see, it's sort of equivalent to what we did earlier, isn't it? Because the square root of this binomial means the binomial raised to the 1/2 power, and the reciprocal of that is 2. So squaring on both sides is what we're going to do. Now let's understand, though, that if this were the cube root of the binomial, we would cube on both sides. To undo the cube root, we would cube. Well, it's square root, so we'll square on both sides. So here's what we're doing. Now, on the left, 2x all squared is 4x squared. On the right, when we square the radical, you see, what we get is the radicand. All right, so we have 4x squared is equal to 15 minus 4x. Oh, yes, this is a quadratic equation. So we throw all the terms to one side, adding 4x and subtracting 15 on both sides, we get this. Now we factor as we normally would. Well, the factors are 2x plus 5, 2x minus 3. And we set each factor equal to 0. You see, we're changing it from a sort of a quadratic equation into two little linear equations, setting each factor equal to 0. We'd like to know the x that causes 2x plus 5 to be equal to 0. So solving this little linear equation, we find x to be negative 5/2. And here we set this factor equal to 0 and solve, and we find x to be 3/2. It turns out that both of these are valid solutions. And it's important to check the answers when pulling these little shenanigans about squaring on both sides and that kind of thing, because as we said, you can create erroneous solutions that way. All right, here's one involving two radicals. Now, our prescription when equations involve radicals is to isolate the radical and square, if we're talking about square root. Well, here we can't isolate because we have two of them. So what we have to do is isolate one of them and still square on both sides. Let's see what happens. Here, you see, we're going to isolate one of these, and I'm going to isolate this one. Now, you can choose to isolate either one that you like, but you need to isolate one of them. At any rate, I'm isolating this one. Now what I'm going to do is say, all right, I want to eliminate this radical, and to do it, I'm going to square on both sides. Now, notice I'm also squaring this coefficient. All right, and over here, I have to square also. But it's not just a matter of squaring every single separate term. We're squaring the entire side of each equation, which makes for an interesting situation on the right. Well, we'll deal with that in just a second. Let's come back over here. Square the 2 and we get 4. Square the radical, you see, and we get the radicand. So this is easy. The radical dropped out. But look at what happens over here. When we square, it means we have two factors of this binomial. Wow, two factors of a binomial involving a radical. So we really have the square root of this thing plus 1 times the square root of that thing plus 1 again. Well, we know how to square. There's a fast way, remember, to square binomials. Let's see. We take the first term of the binomial and square it. Well, square this first term and we get the radicand. All right. The middle term of our trinomial answer, as we think of it, is twice the product of these two. All right? So 2 times this product. This product is simply the radical because it's the radical times 1. 2 times the radical, then, is our middle term. And the last term in squaring is this item squared. So 1 squared is 1. All right, now we've done all of that, but we still have a radical involved in our equation, but only 1. So now we go back to our original prescription for handling this situation, and that is isolate the radical and square on both sides. All right, let's do that. We have some cleaning up to do, though, don't we? So a little bit of house cleaning over here to simplify terms. 2x plus 3, I'll just remove the parenthesis here and bring down the 1. And now, collecting like terms, I have 3 plus 1 gives me 4. All right, now that this side is in simple form, I'm ready to eliminate these two terms. All right, I do that by subtracting 2x on both sides. The 2x will appear as negative 2x on the left. The 4 becomes negative 4 on the left. All right, and of course the 2 times the radical is left over on the right side. Now back to the left, I'm collecting like terms. 4x minus 2x is 2x, and the 4's go out. All right, notice here that I've got this 2 as a factor of the radical, so I'll divide on both sides by 2. And fortunately, I have a cancellation here with it on the left. So when I divide on both sides by 2, I get x is equal to the radical. Well, now I'm ready to square on both sides to clear that radical. Squaring x, I get x squared, and squaring on the right, I get the radicand. And that step is up here. So x squared is equal to the radicand, which is 2x plus 3. And now we see this as a quadratic equation. So we put all the terms on one side. That is, we subtract 2x on both sides, giving us negative 2x on the left. We subtract 3 on both sides, giving us negative 3 on the left. Now, as I'm writing these problems on the board, my equal sign is bouncing around quite a bit. And I don't like that, but I have to deal with it here on the board. My suggestion to you is that as much as possible, if you keep your equal signs lined up, then I find that my students make fewer mistakes when they do that, because they can see where terms are moving from one side of the equation to the other. And actually, they're not actually physically moving, but their opposite appears on the other side when they disappear from one side. But at any rate, this subtracting 2x you see on both sides, the negative 2x appears over here, and the 2x disappears from the right. And really, I should have this equal sign right under here if it's going to be completely clear. But I'd like to point that out here as just a little precaution for you. All right. At any rate, we factor the trinomial. We get x minus 3 times x plus 1, and we find x to be 3 and x to be negative 1. Now, let's check these answers. And I'm checking this one. I didn't check one of the early ones because it was a fraction and we had higher powers and whatnot, so it was a little bit difficult just to think through. This one we can think through, though. Let's see. If x is 3, let's go all the way back to the original. If x is 3, this is 3 plus 1, 4. The square root of 4, 2. 2 times 2, 4. So this is 4. All right, x is 3. 2 times 3, 6, and 3, 9. The square root of 9, 3. So we have 4 minus 3, that's 1. 1 is equal to 1, yes, that checks. Now, I did it mentally, but and it could, of course, be written down, but at the very least, we should do this, particularly on a test. What about negative 1? Negative 1 is another supposed solution. Let's see. Negative 1 in place of x. Negative 1 plus 1 is 0. The square root of 0 is 0. 2 times 0 is 0. This term goes out. It's out of here. All right, so here. 2 times negative 1, negative 2. Negative 2 plus 3, 1. Square root of 1, 1. Minus 1 is equal to 1? No. So negative 1 is not really a solution. So we have to take this one out. This problem, this equation, has this solution and not that one. Another problem. This is one similar to one we had earlier. Notice we have this trinomial raised to the 4/3 power, and that amount is set equal to 16. Well, we resort to we pull out of our mathematical tool chest this idea that we can take one side of the equal sign, one expression on a side of the equation, and raise to whatever power we care to. And what we're going to do is decide to raise this side to the reciprocal exponent, because we know that multiplying or raising powers to powers means multiply exponents. And we know that when we multiply reciprocals times one another, we get 1. And that's what we want to happen, is for this exponent to disappear. So we're raising all of this to the reciprocal exponent, to the 3/4 power. All right, 4/3 times 3/4 is 1. So what we have left on the left side is this trinomial. That's nice. Now, though, raising the left side to the 3/4 power means we need to raise the right side to the 3/4 power. All right, the 3/4 power means that we have to take 16, we have to cube it, and we have to take the 4th root of it. Well, the 4th root of 16 turns out to be 2, and 2 cubed is 8. So this amount turns out to be 8. Okay, 4th root of 16 is 2, and then 2 cubed is 8. That's how we got that. All right, now with this equation, we subtract 8 on both sides, so we get x squared minus x minus 30. Factoring x minus 6 times x plus 5, and the values of x that cause each factor to be 0 are x is equal to 6 and x is equal to negative 5. Now, we might go through the process of checking here again. Let's go back up to the top and do that. If x is 6, 6 squared is 36. 36 minus 6 is 30. 30 minus 22 is 8. Now, we have 8 to the 4/3 power, which means raised to the 4th power, take the cube root of that thing. Well, the cube root of 8 is 2. 2 to the 4th power, 16. So 6 is a valid root. And in checking negative 5 in the same way, we would find that negative 5 is a valid root as well. This equation involves fractions. Now, our fundamental idea with equations involving fractions is to identify a common denominator and multiply throughout the common denominator in an effort to eliminate all of the denominators. So we'll no longer have an equation involving fractions. All right, here, in order to identify the common denominator, we have to be looking for factors. So in our first step, we'll factor. Factoring x squared minus 4, we get these factors. Now, looking for a common denominator, we're identifying every different factor that we see. We see x plus 2, it's in the common denominator. We see x minus 2, it's in the common denominator. We see x plus 2, well, we already mentioned it. So these two factors are the factors involved in our common denominator, x plus 2 and x minus 2. Now, the toughest part of this problem is to discipline yourself to write the next step. And the next step says you show that that common denominator is multiplied times every term in the problem. So we have to march through and show the common denominator times this term, then the common denominator times that term, and then the common denominator times this term further out. Well, once we've shown that step, and it's a long step, I realize, and it's tough to discipline oneself to write this down, but it's an important step to see all of the cancellations easily. Here the x plus 2's go out, the x minus 2's go out, and we have x. In the next part, this x plus 2 will cancel with this x plus 2, and we have 1 times x minus 2. All right, 1 times x minus 2 gives x minus 2. Now, on the right side of the equation, this is what we have. We have the common denominator times 3. All right, now this product is nothing more than x squared minus 4. So we have 3 times x squared minus 4, which is 3x squared minus 12. And that's the right side of our equation now. Well, at this point, we see that we have a quadratic situation. So we'll collect all the like terms that we can. We'll simplify on each side of the equation, and then throw all the terms to one side or the other. X and x is 2x, with minus 2 is 3x squared minus 12. Now, notice what I am electing to do here. I am anticipating that I'm going to try to factor when I put all of the terms on one side of the equation. I'm also anticipating that I would like to have my trinomial in a form that is most factorable. That is, I would like for this leading coefficient to be positive. Now, in order to do that, what I'll do is I'll elect to throw all of my terms to the right side of the equation rather than the left side. You see, if I subtract 3x squared on both sides, I'll have a negative 3x squared leading coefficient on this side of the equation. So I can anticipate that and subtract 2x on both sides and add 2 on both sides and get this. See, the 3x squared comes down, the negative 12 comes down, the subtracting 2x gives me minus 2x on the right, adding 2 gives me plus 2 out here. All right, now I can collect like terms. These two terms are alike, and I'll get negative 10 for the constant. All right, let's do that up here. Now, here's my new equation. It's clearly a quadratic equation, and try as I will, I find that I can't conveniently factor this thing. So what I need to do is go to the quadratic formula. Well, the quadratic formula, that's x is equal to the negative of b plus or minus the square root of b squared minus 4ac all over 2a. So I write that down, and then I replace letters with numbers, and that's all in the first step. So b is the negative 2. So the negative of b is the negative of negative 2. And then this b squared is negative 2 all squared. And then minus 4 times a is 3. And c is the negative 10. All right, and in the denominator, 2a means 2 times 3. All right, now we begin to simplify. Now this other part of the problem is sticking in here. Let me remove it for simplicity. All right, we've got the negative of negative 2, that's 2, plus or minus. Negative 2 is squared, that gives 4. This product, negative 4 times 3, would be negative 12. Negative 12 times negative 10 is positive 120. 120 and 4, 124. But 124 contains a square. 4 is the biggest square, it turns out, in 124. So 124 we factor up here into 4 times 31. All right, now the square root of the 4 part gives 2 on the outside of the radical, and 31 is left under the radical. Now, to reduce just a bit, we'll factor in the numerator. Taking out a common factor, 2, we get 1 plus or minus the square root of 31. Now, 2 into 2 goes 1, 2 into 6 goes 3. So we have 1 plus or minus the square root of 31 all over 3. Now, using a calculator, we can verify that this answer works in our original problem. Now, we came a long way with this problem. There was a lot of discipline involved in getting to this point in this problem. A lot of organization, a lot of writing large and understanding what we have from step to step and just kind of thinking our way through it. Well, let's turn our attention to another kind of problem. This kind involves absolute value. Absolute value problems can be viewed in a number of different related ways. One way is like this. Suppose I say that the absolute value of x is equal to 5. Now, all I'm trying to do is solve the equation. That means I'm trying to find a replacement for x that makes this true. Well, what x replacements here would make this statement true? X, you see, could be what numbers? Well, the absolute value of 5 is equal to 5, but the absolute value of negative 5 is also 5. So this x can either be 5 or negative 5. Now, that notion is the basis upon which many absolute value equations are solved. Here's one, for example. You see the absolute value of this amount, and you can think of it just like I thought of that one up there, like just as one single letter or one single number. This number in here, you see the absolute value of whatever number this is going to be equal to 3. Now, what number goes in there? Well, either a 3 or a negative 3 goes in there. So we can say then that this x minus 2 is either really just a 3 or it's a negative 3. And we can therefore set up two equations that correspond with that understanding. So we would say then that one solution is found if x minus 3 is equal to 3. Another solution is found if x minus 2 is equal to 3. I misspoke there, I think, and called that a 3. At any rate, if x minus 2 is equal to negative 3, we also have a true statement. So notice that the problem is really splitting into two cases here. And this is often true with absolute value type problems. Now, each of these cases can then be solved, and we find x to be either 5 or negative 1. Now, notice that they work. If x is 5, we have 5 minus 2 is 3. You see, so the absolute value of 3 is 3. Here, if x is negative 1 with negative 2, that would give negative 3 inside. So the absolute value of negative 3 would also be 3. Consider this absolute value equation. Now, we'll approach it in much the same way we did the previous couple of problems. We're thinking, gee, the number inside this absolute value symbol is either the same number as the number over there, or it's the negative of that number over there. You see, so we split into our two cases. One case is where we just set this number equal to that one. That is, x squared minus 3x is set equal to negative 4x plus 6. All right, and then we work through. Now, we notice we have a quadratic equation here. We throw all the terms to one side. Adding 4x on both sides and subtracting 6 on both sides gives us this. Collecting the x's, we get an x. Negative 3x with 4x gives us x. And now we factor into x plus 3 times x minus 2. Our potential answers are x is equal to negative 3 and x is equal to 2. Now I say potential answers because what we've done is we have solutions to our quadratic equation here. And we are not sure that we have solutions to our absolute value equation. Now, the thing about checking these, there are a couple of ways of checking. One way, the surefire way, of course, is to replace x with the negative 3 everywhere we see an x up there. And then replace all those x's with the 2 and just see if we have truth in either case. Another clever way to do it, though, is to understand this, that the absolute value of some amount here has got to be positive. Absolute values are always positive. So any value or any candidate as a solution that we find that causes this side of the equation to be negative will not work. It can't work because we're taking the absolute value of some number here. All right, well, let's use that theory here. How about negative 3? Well, negative 3, I'll test over here first. Negative 3 times negative 4 is 12. 12 and 6, 18. So we get 18 over here, a positive number. Now, that doesn't necessarily mean we have a correct answer, but it means we certainly have the potential to have a correct answer. If this is a negative 3 squared, gives us 9. Negative 3 times negative 3, that's another 9. 9 and 9, 18. 18 is equal to 18. Yes, that one works. So this is a correct solution. What about 2? Well, 2 in place of this x. Negative 4 times 2 is negative 8. Negative 8 plus 6 is negative 2. This side of the equation cannot be negative for this entire side to be an absolute value. No absolute value is going to be equal to a negative number. So this cannot be a valid solution. Very quickly. All right, on this side, now the other part of our two-case situation was that this number under the absolute value symbol is either the same as that number or it's the negative of that number. See? And so here's the case where we're setting up a situation where we're claiming that number might be the negative of that number. All right. So the negative of this number means negative 1 times the binomial, or 4x minus 6. Now again, a quadratic situation, we throw all the terms to one side by subtracting 4x on both sides and then adding 6 on both sides. Now collecting the x's here, we get negative 7x. We bring down the 6 and we do a factorization as we did earlier. So we have x minus 6 times x minus 1 is equal to 0. The values of x that cause each factor to be 0 are 6 and 1. Again, we'll go through the check. If x is 6, look at this side. Negative 4 times 6 would be negative 24, with 6 would be negative 18. Can't happen. We can eliminate that as a possible solution. What about 1? Well, if x is 1, negative 4 times 1 is negative 4. Negative 4 plus 6 is 2. So this side is 2. Potential correct solution. If x is 1 over here, 1 squared is 1. Negative 3 times 1 is negative 3. 1 with negative 3 is negative 2. Absolute value of negative 2, 2. 2 is equal to 2. Correct solution. So this one was correct. Notice that in each case we had one valid solution and one invalid solution. we're including the 3 and not including the 7. So it appears here that 3 is less than or equal to the numbers we're talking about. Let's call them n's. And these n's are less than 7. And in interval notation turns out to be even easier than building inequalities, because all we do is we say, okay, we're talking about the numbers between 3, comma, and 7. And we indicate whether the end points or those bounds are included in our set or our interval. The 7 is not included, so I'll indicate openness on that end and closed situation on this end. Well, let's see. How about this third one? We have an interval notation that says 4, comma, infinity. So we want to indicate all the numbers from 4 to infinity and including the 4. Well, let's see. The inequality then would be numbers that we'll call, let's call them r's. R then is greater than or equal to 4. The numbers to the right and equal to 4, you see. All right, then the graph, let's indicate where 4 is and a couple of reference points. Now, numbers that are greater than or equal to 4, we want to include the 4, so we'll put a bracket here at 4, and we'll shade the numbers to the right of 4. And it goes on forever. All right, with that in mind, now we have the ability to show a solution set in a number of ways. All right, let's talk about solving inequalities. It'll turn out that with linear inequalities, we solve them in much the same way that we solve linear equations. That is, we can add on both sides of an inequality symbol, and we can subtract and multiply and divide. There's just, well, I guess 2 exceptions to that, and we'll look at the exceptions momentarily. I'll tell you what they are right now. If you have occasion to either multiply or divide by a negative amount, then the sense of the inequality has to change. That means that the direction of the little arrow has to change. Well, we'll look at that shortly. Right now, let's just look at this inequality, and if we bump into that situation, we'll deal with it. But here, just imagine the problem without the inequality symbol. If we had an equal sign here, what would we do? Well, we would want to put our unknowns on one side and our constants on the other side. So in order to accomplish that, we'd subtract 3x on both sides. This 3x would disappear, and a negative 3x would appear on the left. We'd like to clear this negative 7, so we'll add 7 on both sides. Adding 7 here clears the negative 7, and plus 7 appears on the right. Now collecting like terms. 5x minus 3x is 2x. 9 and 7, 16 on the right. Now what we need to do is divide by the coefficient of x. That coefficient is 2. Dividing by 2, we find x to be greater than 8. Now, x is greater than 8. We have an inequality that is being described here. We could also construct the graph. We could also use interval notation, as we saw earlier. But understand that we're talking about an awfully big set of numbers that make this original inequality true. The idea of solution here is very similar to the idea of solution with equations, and that is that we're looking for a value of the letter that causes the inequality to be true, and we simply want to list them all. And now checking it is somewhat challenging, isn't it? Because we can't very well replace x with all of the numbers that are greater than 8. However, what we might do, just to make sure that what we have makes some sense, is choose 1 or 2 numbers larger than 8 and plug them in and see if we have truth. Now, if x is 10, you see we'll have 5 times 10 minus 7. Now, 5 times 10 is 50. 50 minus 7, 43 on the left. And we want to see if that's greater than 3 times 10, 30. 30 plus 9, 39. 43 is greater than 39, so we have truth if x is replaced with 8. Okay, so this is a reasonable, it's reasonable to assume that this may very likely be a solution. All right, let's consider another situation here. Suppose we have this inequality. Now, notice where we are led in this problem. We would isolate the x term by subtracting 4 on both sides. Then collecting on the right, we would get negative 1. Now we have the occasion to divide by negative 2. Here's what we need to write. When we divide on the left by -2, and we're going to indicate the division of -2 on the right. It turns out that we change the sense of the inequality, or change the direction of the arrow. And we'll talk about why in just a moment, but to finish it out, we get the cancellation here and we find x is greater than 1/2. Greater than 1/2. Well, we could choose a number and see if we have truth here. 1 is greater than 1/2. Let's see what 1 does up here in the inequality. 4 minus 2 times 1 would be 4 minus 2, or 2. 2 is less than 3. Yes, that's true. Okay, now why is it that we need to change the sense of the inequality? Well, look at this situation. Suppose, now we know that, that 1 is less than 5. Look at what happens if we multiply by, just say -1 on both sides. 1 times -1, is that less than 5 times -1? Well, 1 times -1 is -1. 5 times -1, -5. Is -1 less than -5? No. You see, what happens when we multiply by -1 is that we are really creating the opposite of the number that we had before. And on the number line, when we look at the opposite situation and throw a number way over on the number line to its opposite, we are changing their relative positions. We are changing their order. And so we have to change the sense of the inequality. All right. That means then that it's pretty important to write this step, to write the step where you're showing what you're dividing on both sides. And it's important to get into the habit of showing that step before you're faced with a situation of dividing by a negative. Here's an inequality involving a fraction. Now, we approach it in the same way that we would approach an equation involving a fraction, and that is, our pattern, our prescription, is to multiply through by a common denominator to clear the fraction. Well, let's see. We'll multiply through here by the common denominator 2. So we show that 2 is multiplied times every term. 2 times x, 2 times the -4. Notice here, when I show that 2 is multiplied times this term, I'm just injecting a 2 factor in between this sign and the 3x over 2. And I'm just pumping in a factor of 2, you see, right into that term. There's no need to get complicated with the idea of thinking of it as a +2 times a -3x over 2 and that kind of thing. Don't make it more difficult than it is. It's just popping in a factor of 2 in order to clear the fraction. All right, so we have 2 times 1, 2. The 2's cancel here, leaving -3x. 2 times x, 2x, and -2 times 4 is -8. Now, let's throw the x's to the left side. Let's see what happens. We'll subtract 2x on both sides. That'll give us the -2x on the left. I'll bring down the -3x. At the same time, we want to clear the 2, so we'll subtract 2 on both sides. That'll clear the 2 over here and create a -2 on the right. Collecting like terms, we get -5x on the left. We get -10 on the right. Now, notice what has to happen. We have a negative coefficient. So that tells us that when we indicate the division of that negative coefficient, we have to change the sense of the inequality. And then we perform the division as we normally would to find x to be less than or equal to 2. Now, here's the part of the problem that's often missed and often left out and so forth. And it is really the division by the negative that creates the difference between the equations and the inequalities, the linear ones. And actually,